All right, so first, just some news. The first test is Monday. And the topics for this test are everything that we've done, everything you've done problems on up through particle kinematics in non-rotating coordinate systems. So Monday is what would that be? It's the 5th? Is that right? Yes. Awesome. Okay. Any questions about the test right now? I mean, I'd be happy to, on Friday, be happy to take questions related to it also, but yeah.
Would the best thing to study for that would be like all the homework problems?
Yes, that's right. The best way to get ready for this is to just know the approaches to all the homework problems, all the daily assignments so far. And so what I would recommend doing, if you can find the time to do it, is go back to the beginning and look at each question one by one and ask yourself, do I know the steps here? And if you know the steps for that one, you can say like, okay, you do this, you take the cross product, you do that, but then don't waste any more time on that because you know it pretty well. But wait till you get to the ones where you're a little hazy, and then maybe spend a little time working through those, remind yourself. But I always think of it like this. This is when you're ready to ace this test. If you could, any question that someone picked out randomly, if you could do it and answer any questions they have about why you did this, then you'll do great on the test. Okay? The approaches that you use on the homework are the same as the approaches you'll use on the exam. Any other questions just about the test? And then also, I put up the first weekly assignment. And because we have a test next week, and we also have a test in D-form for the people in D-form, I gave you extra time for this. So this is due, I believe it's Monday the 12th. And remember that you can talk to each other about this to figure out how to do it, but then you need to go off on your own and do this test. It needs to be your own work that you turn in. You can talk to people to understand how to go about it, but you need to do it yourself, And yeah, that's about it on that. Any questions about the weekly assignment right now? You haven't seen it yet. Okay. Anybody have any homework questions you want me to go over? Yes. Number 4? 24. Come on. Oh, yeah. Okay, so this is sort of a conceptual question. So Okay, so this is particle kinematics. Number 24. And the question is basically, why can we use relative motion for a problem like this? Okay, where this point is moving in a circle like this, right? And the little one is moving in a circle about its point like this. Okay, we can do problems like that. I've assigned you a whole bunch of them. We've done 1 or 2 in class, right? But we can't use relative motion for problems like this. Okay, where still this point here is moving in a circular path like that. But this one isn't moving in a circle in this plane, it's moving out of the plane. Okay? And the answer basically is that in problems where the two circular motions are in different planes, notice that the axis of rotation, and actually let me set you up for the way we're going to think about this later on. So there's always one body that's motion is independent of the other one, and then the second one rides the first one. Okay. That's true in the first example too, right? Here you have the horse is the one connected to the floor, and then the cowboy is the one connected to the other end of it. You know, you always have one riding the other one. Don't think of that song about the horse riding the cowboy. That'll mess you up. But in every other song or picture, the cowboy is riding the horse. You know. So notice that in cases where the two circular motions are in different planes, the cowboy's axis of rotation changes as the horse rotates. Okay, so at this So this is just a picture of this motion as this thing swings around and this thing swings around. But notice in the next instant, maybe the horse is at this angle, okay? And now this thing is rotating about a different axis, okay? So that's why that gets complicated. Look at, now, compare that to the case that we can do. The horse in the next instant is still at a different angle, but as that angle changes, the axis of rotation here still keeps pointing out of the page. Okay, you with me on that? And so that's what allows us to do this. The axis of rotation of this circular spherical motion doesn't change over time. Okay, we're gonna have to use a whole new approach when we get to stuff like this. Okay, this we're gonna have to use rotating coordinate systems. Because, so how is the rotating coordinate system thing gonna come up? Well, we're going to define our coordinate system with one of the axes, say the y-axis or whatever, pointing in the direction that this one rotates. We're going to do that so we can represent this as circular motion. Okay, but that means that this axis is going to change its orientation, and so we're going to have to use rotating coordinate systems, which is going to, if you go back to like the first lecture in the class, I just tried to give you a hint at why coordinate systems that are rotating mess everything up, and we're going to have to use one here in order to calculate the velocity and acceleration at this point. Okay. Any questions about that one? Any other homework questions you want me to go through? Yes.
Just in general, I don't think we've seen, I could be wrong, but I don't think we've seen one of these standard problems with like our acceleration and velocity are always just given as like a numerical vector. There's never any variables in them.
Yeah, I guess that's probably true. You could do, like you're imagining, I mean, you basically just have a whole bunch of equations, and you could set up a problem that's kind of backwards where you're given the velocity or acceleration and you have to back calculate some omegas or something. Is that what you're thinking about?
Okay. Yeah, I mean.
Yeah, I guess I never made a question like that because I never really thought of it before, but you could do that.
Like the watermelon equation work if you had, an omega that had variables in it.
Yeah, that's right. So if you had, let's say, if you had a problem where this thing was you knew the angular velocity of this, and then this one was rotating, but you don't know how it's rotating, it's just some omega. And so given that the acceleration of p is equal to let's see. Well, you could do it actually with two unknowns, I think. So given that this is negative 20, positive 15, 0, what are omega 1 and omega 2? Okay. So here we're assuming that the angular accelerations are both 0. So this would be G, A, should we do one like this? Maybe we should do one with a velocity because we haven't done that yet. Well, no, let's just sort of think about how you would set this up, and then I'll go on to other example problems. So the acceleration of A relative to G would be equal to alpha 1 cross R1 plus omega 1 cross quantity omega 1 cross R1. This would go away. This goes away because there's no alpha, just the way I set it up. And so this comes out to be 0, 0, omega 1 cross quantity 0, 0, omega 1 cross, what would that be? I didn't give lengths, but let's say we know the length. And you get something like 0, 2 omega 1, 0 for that. And then for the whole thing, you get negative 2 omega 1 squared, 0, 0. And now we'll do acceleration of P relative to A. So that's the circular motion of this one. Okay. You get something. I did that at a funny angle, so now, but this is going to be a vector that has omega 2 in it. And then use relative motion, and you have an equation, two equations, because there's two non-zero components, x and y, and you can solve them for omega 1 and omega 2. Yeah, you could do that. I don't think I've done any problems like that, though, and I'm not going to put it on the test, so. Any other homework questions? Okay, let's do an example where we calculate the velocity, because we haven't done that yet. And then I need to make sure I get to rolling without slipping too before we finish today. Okay, so let's say we have a meter-long member like this, and a meter-long member like this. And let's say that this one has an angular velocity in this direction of 5 radians per second. And this one has an angular velocity of 10 radians per second. We're going to assume that these angular accelerations are 0, which means there has to be some kind of motors or something in there to keep gravity from giving this an angular acceleration. So this is part of some kind of machine or whatever. And let's say we want to calculate the velocity of that point P and the acceleration of that point P. First of all, this is just kind of an intuitive thing. There's no angular accelerations. So does that mean that there's not going to be any acceleration of that point P or this point A? I'll call that G, call this A. It doesn't mean that. That's an easy mistake to make, but remember that for circular and spherical motion, the acceleration is made up of a tangential part. That does depend on angular acceleration. But then also plus a centripetal part that doesn't depend on the angular acceleration. So in a problem like this, where there's no angular accelerations, we're just going to have a zero first term of the acceleration equation, but a non-zero second term. Okay, so let's do the velocities first. So we know that the acceleration of P, and you can always think of that as relative to the ground. No, I'm doing velocity. The velocity of P relative to the ground is equal to the velocity of P relative to A plus the velocity of A relative to the ground. Okay, so velocity of A relative to the ground, that is equal to the angular velocity of the first body crossed with R. And so first we have to figure out what this omega 1 is. That's the one that's going to take this 5 radians per second into account. Okay, so what is that angular velocity as a vector?
0, 0, -5.
Perfect. 0, 0, -5. You see that with the right-hand rule? So yeah, make sure that makes sense to you. So 0, 0, -5. Oh, and I said these lengths are both 1, but I didn't write it down. So let's say L1 is equal to L2 is equal to 1 meter. Okay, so the definition of that R vector is from the center of the circle or sphere to the point at the instant that you're doing the calculation. So for us, that's going to be 0, -1, 0. Take that cross product and you get -5, 0, 0. This is in meters per second. You can sort of eyeball that and make sure it makes sense. Since this thing is moving in a circular path this way, the velocity is going to be tangent to that circle, so -x direction. And now we'll calculate the velocity of P relative to A. That's equal to omega 2 cross R2. What I wrote here is not accurate. Okay, so the velocity of P relative to A is equal to, we have to figure out omega 2 for that second body. So according to the right-hand rule, what's that? Yeah, 0, 0, -10. Crossed with, what's the R vector? So now, anytime you're thinking of a body relative to a, something relative to a point, you can think of that point as fixed for that calculation. That's sort of what we're doing, is that like you don't notice what that point is doing. Yeah.
Wouldn't the angular velocity be in the y direction, not the z direction?
It depends on what your coordinate system. I'm thinking of it like this. So the z direction is coming out of the board.
Okay. Useful perspective.
Yeah. Okay, so the r vector goes from the center of this circular motion, which is A, to the point P. So that's going to be 1, 0, 0. And so that is 0, negative 10, 0. And now the velocity of P, which implies relative to the ground, is equal to 0, negative 10, 0, plus negative 5, 0, 0. So negative 5, negative 10, 0. Any questions about that first part, calculating the velocity? Okay, so now we're going to do the acceleration. And the acceleration of P, which implies relative to the ground, is the acceleration of P relative to A plus the acceleration of A relative to G. The acceleration of A relative to G is alpha 1 cross R1 plus omega 1 cross quantity omega 1 cross R1.
Gaia,
Yeah.
can you look at, can you just scroll up a tiny bit? So for velocity of P with respect to G, is that, what's the first vector there?
Velocity of, that's the velocity of P relative to A.
Oh, I'm a step behind, sorry.
Okay, well, there's no angular acceleration here, so that part is equal to 0. We've already figured out what these are, so this is going to be, I don't remember what it is though. 0, 0, negative 5, crossed with the quantity 0, 0, negative 5, cross 0, negative 1, 0. And we've already calculated the stuff in parentheses. So that's negative 5, 0, 0. And so that is 0, positive 25, 0 meters per second squared. Any questions about that one? And now we'll do the second one, the acceleration of P relative to A is alpha 2 cross R, all right. Watermelons will rot. Omega 2 cross R2 was 0, negative 10, 0. This one goes away. Um, so we got 0, 0, negative 10 crossed with 0, 0, negative 10 cross 1, 0, 0. And we get negative 100, 0, 0. And so put those two together, and the acceleration of p is equal to negative 100, 0, 0 plus 0, 25, 0. Any questions about that? You also can have cases where the angular velocity is instantaneously 0 and the angular acceleration is something. And so those are things that I can do to simplify the arithmetic a little bit. Like, for example, on a test, I do that kind of stuff a lot. So get rid of one term, cuts the stuff you have to calculate in half while still it's still the same idea, the problem. So, yeah, be ready for that. Okay. Let's talk about rolling without slipping. That's the last topic for this stuff. And what I'm doing this for is only circular and spherical objects rolling. So, egg-shaped things can roll. Anything that doesn't have that isn't flat can roll. But this is not dealing with ellipses or egg shapes or anything like that. It's just circles and spheres. Okay? Triangles don't roll. What? I guess, yeah, you're right. They can roll. You can roll a triangle. Okay, well, this doesn't do triangles either. Okay, yes, you can. You're right. You can roll them. So what does it mean that it's not slipping? Mathematically, it means the following. The part of, so at the point that's in contact with the ground, the component of the velocity that's parallel to the ground is 0. So, I mean, you can think of that as just literally like a mathematical description of what it means for this thing not to slip. The point that's in contact with the ground has to have the same velocity as the ground. You know what I mean? Otherwise, it's slipping at that instant. Okay? Otherwise, it's sliding along the surface. And the same has to be true with the component of the acceleration that's parallel to the ground. So the component of the acceleration parallel to the ground is 0. And I used to make people go through, like, learn how to derive this, but I'm not going to do that anymore. I'm just going to tell you that the derivation comes from these two requirements and then relative motion, like you would imagine, you know. So if you have an object rolling along a surface, and the center is, we're going to call that C, okay? First thing you want to do is set up your coordinate system with the x-axis. Well, think of the y-axis as coming directly out of the surface. This is like the orientation of the coordinate system that you used for sliding blocks and inclines in Physics 1. Okay, so y-axis out of the surface, x-axis along the surface. That means, in this case, that the z-axis is coming out towards us. Then, if you think of omega and alpha according to their components, you know, a positive z component of omega would be this way. Then the velocity of the center of that sphere or circle is negative omega r for an x component. Let's, I'm sorry, I'm messing up your notes here, but let's call that a capital R to distinguish it from what that lowercase r meant in the acceleration equation. And the acceleration of the center of that thing is negative alpha r 0, 0. Why the negative sign? Well, you can see if we have positive values of omega and alpha according to our coordinate system, this thing's rolling this way, so it would have to be going up the ramp. Okay. So let's use these in some calculations.
That negative sign is the only reason things don't roll uphill.
Yeah, you're right. That's the only thing holding us back. That's true. That's a really good point.
Right now?
God, things would go crazy. Everyone would wonder what just happened. All right, so if you have a wheel rolling around along the ground, and let's say we have a constant angular velocity of, let's say pi radians per second. And the radius of this thing is, let's call it half a meter. Let's call this point A and this point B. So first we're going to calculate the velocity and acceleration at A. And then second, we're going to calculate the velocity and acceleration at B. All right, so how are we going to calculate the velocity and acceleration at A? So the velocity at A, and if it's not mentioned, that always means relative to the ground, is equal to the velocity of A relative to the center plus the, oh man, the gravity just reversed, I think. Velocity of the center relative to the ground. Velocity of the center relative to the ground. This one just comes from what I told you. So that's just, negative omega r 0, 0. R omega, the way I drew it, is negative. So this is pi over 2, positive pi over 2, 0, 0. With me on that?
And that's in meters per second?
Yeah. Anybody have any questions about that? That just came from the formula I gave you up here. And these formulas on tests and stuff, I'll give you those. You don't have to derive those or anything like that. But so we know what this one is. How are we going to get the velocity of A relative to C? Yep.
Do omega cross r.
Perfect. Yep. That's circular motion. So this is omega cross r. So that omega is 0, 0, negative pi crossed with r goes from the center of that circle to A. So that's 0, negative 0.5, 0. And you get an answer of negative pi over 2, 0, 0. And so the velocity of that point A is negative pi over 2, 0, 0, plus pi over 2, 0, 0, which is zeros. Well, we knew that the part, if it's not slipping, we knew that the horizontal component of the velocity had to be 0. This tells us that the vertical component of the velocity is also 0. So instantaneously, as a thing rolls, every point when it touches the ground has 0 velocity. And actually, you can see that, I should have pulled up a picture like this, but if you take a somewhat long photo exposure of a wheel that's rolling, the stuff on top will be really blurry. The stuff everywhere else will be a little blurry, and the spoke or whatever that's touching the ground will be crystal clear, because right at that instant, that point has no velocity. At the next instant, it will have a velocity, and some other point will have 0 velocity.
Mm-hmm.
Okay, what about the acceleration? So the acceleration of A relative to the ground is equal to the acceleration of A relative to the center plus the acceleration of the center relative to the ground. This is moving with a constant angular velocity, so there's no angular acceleration. So this is negative alpha r 0, 0, which in our case is zeros. So in order for the center of a wheel or whatever to be accelerating, there needs to be an angular acceleration. That makes sense, right? And the acceleration of A relative to C, that's circular motion. So this is going to be equal to all ripe watermelons will rot. There's no angular acceleration. So this is 0, 0, negative pi crossed with 0, 0, negative pi cross 0, negative 0.5, 0. And if you calculate that out, you get 0, pi squared over 2, 0. And so the total acceleration of A is 0, pi squared over 2, 0, plus 0, 0, 0. And so for the acceleration, we did get that there's no horizontal acceleration, which is what's required for it not to be slipping. But notice there is an upward acceleration of that point, and that comes from centripetal acceleration of the wheel. Okay. Okay, one more quick thing. Forget about the acceleration at B, but you would do that the same. But I just want to show you one more thing. Let's calculate the velocity of that point B at the top of the wheel. Okay? So velocity of B relative to the ground is equal to the velocity of B relative to the center plus the velocity of the center relative to the ground. Velocity of the center relative to the ground, just like it did before, comes from negative omega r 0, 0. And so this is pi over 2, 0, 0. Velocity of B relative to C is omega cross r. Omega is 0, 0, negative pi. R for a point at the top of the circle is 0, positive 0.50. And so the velocity is positive 0.5 pi 0, 0. And so the velocity of B is pi over 2, 0, 0, plus pi over 2, 0, 0 is equal to pi 0, 0. In other words, the top of a wheel, the top point of a wheel is always moving twice as fast as the center of the wheel.
And the acceleration would be the same, but in the negative y direction.
Yeah, exactly. Okay, and so when, you know, a huge part of the game of like bicycle racing is aerodynamics. One of the reasons that when you're thinking about aerodynamics, you have to put special attention into the aerodynamics of the wheels is because at every instant, the stuff on the top part of the wheel is moving twice as fast as the bicycle is, okay? And remember that air resistance increases as the square of the speed, okay? So increases in speed cause huge increases in drag, okay? So anyways, that's the kind of thing that's important for. Okay, that's all. See you Friday. Yeah, see you in 10 minutes.
I don't know why I thought automatic.